values of HI, BH, and BC. I would say in general, a clue that you want to use at least one section cut in your solution is if they are only asking for specific forces in specific members and not forces in all the members. Probably the first thing you'll want to do is a section cut and then either another section cut or pins after that. Based on the figure, what's the first thing we want to do in solving this problem? See if it's statically determinate. If it is, make that external picture first. So in this case, we have a pin at A, a roller at E. How many supports, external supports, does that give us? Or reactions does that give us? 3. Right, 3, it's statically determinate. So before deciding about internal things, I'm going to draw that external picture and solve for those first. So my first free body diagram, I take my entire structure and release it from the pin at A, release it from the roller at E. I have that pin AXAY at A. I'll call it EY at point E. And I have these 4 applied loads on top of 30. These are all kilonewtons, but just to save a little bit of space here, I'll just write their numbers. And for the purposes of the external picture, it really doesn't matter what the cross trusses are in the center. That's not going to affect the external picture at all. So really just a simplified picture here is going to be fine of the general shape, where the forces are being applied, and where the supports are located. Because it's statically determinate, I can use this to find my reaction, the support reactions. So in picture 1, the first thing I can see is the x direction. AX is going to be 0. It's the only force acting along the x direction. Because I have a pin, I'll do a moment equation next around A so that I can find the value of EY right away. So around point A, I'll have 16 times EY. The 30 kilonewtons acts through A, so it will not contribute to the moment around A. The 20 kilonewtons is acting 4 meters from A, and it's going to be clockwise or negative around A, so minus 4 times 20. Minus 8 times 20. Minus 12 times 40. Some of the only unknown by design is EY. So the reaction at that roller, I am going to find to be 45 kilonewtons. And finally, in the y direction, this is where I have my AY and my EY, minus 30, 20, 20, and 40. AY then is going to be 65 kilonewtons. And we'll see why this external picture, starting with that, is going to help us then in that next step. Any questions on the external free body diagram? Again, always make the assessment with these truss problems. If it's statically determinate, this is always going to be a good first step for what you're looking for, is to get those supports. All right, now we have to formulate a strategy of how to find the, in this case, 3 forces that we're interested in. So we want to start with, can we cut through as many as possible with a single cut? Right, so this one's fairly obvious. We can cut through HI, BH, and BC, and then we can take everything to the left or everything to the right as our picture. And either picture is going to be okay to use because both of them will feature these 3 forces. So as a rule of thumb, I can make that cut, As a rule of thumb, take the side that just has less going on. So the smaller side, it's just going to make your equation smaller to write. So I would say I would prefer to keep everything to the left just because it contains less of the structure. But sometimes you could have a lot more forces happening on one side than the other. So when you think ahead, I'm going to have to write equations from this. So the fewer forces, the fewer things I'm going to have to write and calculate. So in my picture, I took everything to the left of my cut as my free body diagram. But again, you could take everything to the right and you'll get the same answer, just different equations. So in my sectioned picture, I'll take everything to the left of the cut that I'm not cutting through and I copy it exactly. So all these points between A and B and J and I are intact. They're not being cut through. And I'm going to copy exactly any forces that are acting on those joints. And then at A, I have to copy the forces from the pin that was acting at A. So I found AX, AY. AX was 0, so I won't put it in this picture since I know it's 0. But the value of AY I know was 65 kilonewtons. So that is also included in my sectioned picture. So the two external forces and that support reaction at A are in my picture. Now I need to include the forces in the members that I cut through. I have the force in HI to the right, the force in BC to the right, and in this case the force in BH, that again here is at a 45-degree angle, since this is 4 high and 4 long. So conveniently it's 45 degrees. I have that FBH. This is another case where we can make that one cut that goes through the three members we're interested in. I will keep reiterating that's not always the case. You might need to make multiple sections or a section and then a pin diagram. And we'll see that on Wednesday example where we can't just do it with a single cut there. Based on my picture here, just the similar strategy to what I saw in the last one. I'm going to start with sum of forces in the Y so that I can find the value of FBH right away. I'll have 65 minus 30 minus 20 plus 1 over root 2 FBH. So again, by design, FBH is my only unknown in my first equation. So the force in that member is going to be minus 21.2. And we're in kilonewtons. And it's negative, so that's compression.
Moment about B.
Right, moment around B makes sense to do next, because it eliminates, again, 2 of my unknowns. And that's equal to 0. So actually it eliminates 2 unknowns, and the 20 kilonewtons passes through B, or its line of action passes through B, so it will also not be in this moment equation. So the only things in this moment equation around B, I'll have FHI, which according to my picture, since this is 4 meters, and this is 4 meters, right, it'll be minus 4 FHI. I'll have the 30 kilonewtons, 30 times 4, minus 65 times 4. Conveniently in this one, because of everything is 4 meters apart, the 4s all drop out. So based on 5, FHI, I get a negative 35 kilonewtons. So this too is in compression. Right, we have FHI, so last piece of this, summing forces in the x direction in my figure 2. FBC, my last unknown. FHI to the right, according to my picture, plus 1 over root 2 FBH. So plugging in those numbers and then solving for my last unknown of BC, I get that BC's in tension 50 kilonewtons.